So we had an issue with quicksort before, and I had actually solved this in between the first time and the second time that I attempted this, and that my first attempt got wiped. So the issue was this line was outside of the if statement. So I changed the if statement back to if the low index is less than the high index, which is what I had originally published. And then changed things the second time. But this absolutely works if you have the if statement from before and it surrounds all three lines of the quicksort. That was the only change that needed to happen. After that, it works. You can see the output is a sorted array from my example here of 3, 2, 5, 1, 4, quick sorting, and then printing out the 2 string of that. But that was the only change that needed to happen to make the quicksort work. With all of that said, are there any questions about quicksort and quicksort's implementation? Is that a hand, Riley?
It was already pumped.
I'd have to look at any differences between your code and mine. I don't think I made any other changes to my code. That looks the same. I decided against the temp. I guess I don't need that. So we can look at this in office hours, see if there's any changes between your code and mine, make sure that it works and sorts. Actually, it's not what I want to start with. There were 2 more slides I wanted to talk about in. All right, so last time we talked about traversals, tree traversals, and we talked about how to implement tree traversals. We found that the recursive methods were about 5 lines if you included the if statement that surrounds each of the 3 lines of actual execution. So they were very straightforward. I'm not going to do too much implementation of trees because I want that to be your next assignment, and I feel like that's a very big, important part of data structures. So your next assignment after the one that is due on Wednesday is going to be implementing a lot of a tree and insertion and deletion from a binary search tree, as well as the ability to traverse in each of these ways. So I don't want to do too much, and it's not like there's 2 ways to do it where I can demo one and then have you do the other. It's kind of a, there's one way to do it. If I do it here, I can't have you learn it yourself. That said, the next thing that we talk about is something that I absolutely can implement, and I'm not planning to assign at all. So I'm hoping that some of the logic in between this will help. That said, there are 2 things that I want to go over before we leave trees for now. And that is how to search a tree. You search a tree in the same way that you traverse a tree, but you can think about there aren't quite as many ways to search as there are to traverse. Some of them are just kind of the reverse of the other. So to be able to write something like, does this tree contain a particular value? Well, we need to be able to determine if it exists in the tree. Now, I'm not necessarily talking about a binary search tree here where we can always compare less than or greater than and know which subtree to go down. If this is not a binary search tree and it's just a binary tree with integers and we don't know any particular ordering to the nodes in the tree, then we want to have the ability to still search the tree where we make sure we hit every single node in the tree. We need some way to exhaustively do that. And there are 2 important ways to exhaustively do that. So 2 main searching algorithms that we could use to be applied to trees, and they look very much like 2 of the traversals. So the first is called breadth first search. You can apply this concept to both trees and graphs, so that's why I'm introducing it with the easier tree before we talk about graphs in the last couple of weeks of the quarter, because we can apply breadth first search to that as well. So to implement breadth first search, you're going to be using a level order traversal. What was a level order traversal? Who can recall? Yeah, how did we implement that?
Oh, cues?
Yeah, we use a queue. So we have some tree structure, doesn't really matter what it is. You can imagine that we have, it doesn't even matter what data is where. If we wanted to find 5, note that we can't use our usual binary search logic. We can't say, well, 5 is greater than 1, so it's going to be on the right subtree. That's not true in this case, it's down the left subtree. So we need to search the entire tree structure for this value. And we're going to do so using breadth first search, which says, let's just check. Is the root equal to the query data? Is this 5? No. So we're going to add to a queue of 1's children, 2 and 3. We will then take this node 2 off the queue and say, is this data equal to our query, 5? No. We're going to add its children, 4 and 5, to this. Note that now, these are actually node references that we're adding to this. So it's not like we can say, oh, hey, I found the 5. It's in the right child because I'm adding that to the queue. We're adding a node reference to the queue, whereas that data is the 5. And we're not checking the children's data at this point, at this stage. So yes, I'm saying that we're putting this 5 in this queue to look and compare it to 5, but really it is the position in memory where this node is stored. We don't know that it's 5 yet, that the data is 5. All right, so we'll dequeue this node that has 3, check the 3, is that equal to 5? No, it's not, so we're going to add 3's children, 6 and 7. To the queue, dequeue the 4, is it equal to 5? No, it has no children, so we add nothing to the queue. We dequeue the 5, is 5 equal to 5? Yes, we found it, so we can return a reference to this node saying it's right here. And then the program that called this saying, find me the node that contains 5, can do something with that it wants. Maybe it wants to remove that value from the tree. Maybe he wants to duplicate that value. Maybe he wants to report it to a user for some reason. Who knows? But whatever called for this data in this tree now knows where it is in the tree so they can access it and do something with that. Questions on breadth first search? We're basically just, as mentioned, doing a lateral order search through the entire structure. We're gonna look at everything in level 0, then level 1, then level 2, then level 3 in that order. And in general, adding to a queue, dequeuing, and doing that process will do exactly this. All right, that is the first main. What do we think? Are there any pros to doing breadth first search? What are the main pros that we get from this approach?
The whole tree?
We're gonna get the whole tree, well, we hope so. It's not gonna be a good searching algorithm that doesn't get the whole tree. But the main one is that it doesn't search deeper than is necessary. So wherever this node is, we haven't searched anywhere lower in the tree than that. And that way, if you have duplicates in the tree, it returns the lowest, the shallowest value that matches the query. So it also keeps track of a horizon, which means that You're not looking deeper into the tree than you need to at any point. What about cons? Can anyone see the big con with breadth first search? How many elements are in the queue at all times? As you go deeper and deeper into the tree, what happens to the number of elements in the queue? Yeah, it gets more and more and more and more. In fact, it's proportional to about half the number of elements at the end. Half the number of elements in the entire tree are in the queue if the tree is full. And that creates a big memory constraint on breadth first search for large structures. We'll come back to this since I know we're out of time. We'll talk about breadth first search's complexity. We'll talk about the other main search, depth first search. And then we'll start talking about a new data structure that uses a tree visually, not actually with implementation, called a heap. Remember that, please give me your exams back. Don't take those with you. And if you have any arguments for points, you can shoot me in my office and I will happily hear them. That's good.